Hi everybody, welcome back to my channel on Feynman integration. Today we'll be taking a look at kind of an old integral on the channel Flammable Maths. It came up in my feed, so I just decided if I could incorporate Feynman integration into it, even though it's not necessary. He does not use Feynman integration to solve this. But then I thought to myself, well, how could we justify using Feynman integration? And we can do it like this. We can make this integral much more difficult by raising that natural log to some power. I'm going to pick 5. And we will be expressing the answer to this integral as a sum. So the first thing that we need to remember is this, that the sum from n equals 0 to infinity of x to the n is equal to 1 over 1 minus x. So let's go ahead and integrate both sides with respect to x. So that's going to give us this, that the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1 is equal to negative natural log of 1 minus x plus c. If we let our x approach 0, we'll find that 0 is equal to 0 plus c, giving us c is equal to 0. And this will converge on this interval. This will be true for the interval negative 1 to 1. And our 1 is not technically included, but we'll get around that just by assuming we're taking a limit as that approaches 1. So we're good. All right, so now we've shown this. So let's rewrite it a little bit. We'll just bring that negative sign out there. So now we can rewrite our I. Let's rewrite it like this. That means that I is equal to the integral from 0 to 1 of the natural log to the 5th of x, and then we'll have this sum. And we'll bring the negative outside. Negative sum from n equals 0 to infinity of x to the n plus 1 over n plus 1. Okay, so this part replaced this, and then we still are integrating this with respect to x. Okay, now I'm going to perform a little manipulation on this sum. Basically what I'm going to do is I'm going to add 1 to the index on n, and then I'll just have to subtract 1 from all the n's inside the sum. That's a common trick that you can use. And then this will just become x to the n over n. Okay, so that's still true. All right. Now let's use Fubini's theorem on this, basically to switch these sum and integral signs. And let's see how I could rewrite this. Well, let's rewrite it like this. I is equal to negative sum from n equals 1 to infinity. We'll leave the 1 over n outside, and now we'll take the integral from 0 to 1 of natural log to the 5th of x times x to the n dx. And now is the part where Feynman integration becomes very helpful. It becomes helpful in solving this integral, although I don't believe it would be technically necessary to use Feynman integration on that. We're going to anyway, because however you might be able to solve that without it, Feynman integration is going to make it much, much easier. And that's kind of how I justify putting this on a channel on Feynman integration. So let's take a look at this integral. And to start the process of solving this, we'll create a function. This time we'll create a function of n. I usually use functions of t, but you know, it doesn't matter. And we'll set this equal to the integral from 0 to 1 of x to the n. And this will be equal to x to the n plus 1 over n plus 1 evaluated from 0 to 1. The lower bound would cancel out, and you would just be left with 1 over n plus 1, but I'll write it like this. N plus 1 to the negative 1. Okay, and now now it becomes clear why Feynman integration is going to help us. Because if we take 5 derivatives of this, in other words, f quintuple prime of n, we'll get the integral from 0 to 1 of natural log to the 5th of x times x to the n dx, which is exactly what we wanted here. And this will be equal to the 5th derivative with respect to n of this. So what would that be? Well, we're still going to have the n plus 1. That won't change. Taking 5 derivatives, we'll subtract 5 from the index. That will be a negative 6. But what about the constant in front? Well, it's going to be alternating positive, negative, since we're taking 5 derivatives. The first would be negative, positive, negative, positive, negative. So it's going to be negative something. It's going to be negative 1 times 2 times 3 is 6 times 4 is 24 times 5 is 120. So that will be negative 120. Negative 120 times n plus 1 to the negative 6. See, Feynman integration made that integral much, much easier. All right, so now we can rewrite our I using that fact. So I is now equal to, let's see, we still have negative sum from n equals 1 to infinity. We'll still have the 1 over n, but this entire thing will simply become this because they are equivalent. So let's see, the negative and the negative will cancel out. And in fact, I will also bring out the 120. And then what do we have? We still have the 1 over n. And then we have a n plus 1 to the negative 6, but we'll bring that to the denominator as n plus 1 to the 6th. And I don't, please correct me in the comments if I'm wrong, but I don't think you can go any further with that sum. You might be able to squeeze out a pi squared over 6 somehow, some factor of that, by breaking up this sum into a bunch of different sums, but you're still going to have a bunch of different sums to account for, so I don't really think that would be helpful. I think the best way to leave it is like that, and that would allow you to get very, very close to the true answer to that integral. And like if you're an engineering student or a biology student, this is good enough to do anything you would want, to do anything useful with that. So Anyway, there you go. Hope you enjoyed that.